All right, so I want to do number 27 from the homework. And I think this is going to go hand in hand with what we left off in our discussion last time. We were looking at the application of the two-point Arrhenius equation. And I think that's what number 27 is talking about. So we haven't talked about mechanisms yet. And that's our topic for today. But this doesn't deal with that, so. Okay, let's see. All right, number 27 for the homework deals with this reaction here, and it tells you at 25 degrees, the reaction's first order, the rate constant, it gives you the activation parameters, A, the pre-exponential function on the Arrhenius equation, and the activation barrier. And then it asks you to use the Arrhenius two-point equation to find the rate constant at 40 degrees. So we have to remember what that two-point equation is. Excuse me. And make sure we plug in those values in the right positions. So over here, I'm just going to write that down. And let's see if I could just write on that equation what the values that they're giving me. So at 25 degrees, I have a rate constant. So I'll call that pair the first one. And so that would make this rate constant up here 3.4 times 10 to the 14. And that would make this temperature here 25, but I have to convert to Kelvin, so that would be 298.15. Right. Yeah, that's 20. That's 25 degrees. The K2 is what they want to know. The activation barrier is 100 kilojoules. R is 8.314, but I have to convert that to kilojoules. So I'm just going to say times 10 to the minus 3 kilojoules per mole K. And they want to know the constant at 40 degrees, which makes T2 313.15. So now we have everything in the equation. All we need is to calculate is this K2 value. Okay. Any questions so far?
I did it the other way where I converted kilojoules into joules. Is that why I keep getting it incorrect? Like
Yeah. No, it doesn't matter as long as they're consistent. I could have left the R as 8.314 and did 100 times 10 to the 3.
Okay.
Yeah, you should get the same answer.
Okay. Whoops.
And you could try that, just take that ratio, pull it aside, and put the units in as both kilojoules and find the answer for the ratio, and then do it as both joules and find the answer of the ratio, and you should get the same answer.
Okay. So that's not where I went wrong.
Okay, good. So we're still working on that. All right, so if I punch into my calculator, I get for just that temperature term over here, 1.607 times 10 to the minus fourth. So that's 1 over T1 minus 1 over T2. You see it's positive, and it should be because T1 is a smaller number than T2. So when you take the inverse and then subtract them, you should get a positive number. So that's one thing to check to make sure that you did it correctly. Well, just one thing. All right, so I have that. Now I'm going to multiply those two by EA and divide it by R. So I get then minus 1.9324. And that equals the log of K1 over the log of K2. So far, so good?
Yeah.
All righty. And now I want to take the inverse log of both sides and solve for the ratio K1 over K2. And when I take the inverse natural log, what I'm doing is I'm just taking e to this side and e to that side. And so when I do that, that's the inverse function of that. So it gets rid of the ln. It's like multiplication is the inverse function of division. It's just, if you multiply something by 2, you get something, and then you divide it by 2, you get the original number back. So it's just an inverse function, this e. And so when I do that to the other side, I get 0.1448. And I know that K1, remember from back there, this guy is 3.2 times 10 to the minus 3. So I can solve for K2 now. I get 0.022. And I think that's answer A.
I think I switched my K1 and K2 values, and that's why I kept ending up with a different one.
Yeah, it's really easy to do. You know, it depends on the equation you use. When you have a negative sign in this equation outside here, then the 1K goes with this temperature here, and the 2 goes with the second temperature. But if I distribute that negative, then these guys switch.
Okay. Yeah, I think that's what I did.
Yeah, it's easy to confuse those equations. What I do is just I derive them every time, but you don't need to. Just look it up. Make sure you're anal about the negative sign and the identification of the pairs. K1 goes with K2, and well, sorry, K1 goes with T1, K2 goes with T2.
I think I might have missed something. Where did the 3.4 times 10 to the 14th go?
That was down here. Oh, wait a second. Ah, that's the pre-exponential factor A. And so that's not in the Arrhenius 2-point equation. It drops out because you've assumed that that pre-exponential factor is a constant. So it disappears. Let me show you just real quick what I mean. No, let me start here. right? So that's Arrhenius's definition of K. When I take the log of both sides, I get this. Oh, sorry, that's a plus, right? Now, I can do this for two different points. I can do it for the first point, because it's an infinite point function. And then I could rewrite the whole equation and I can put a 2 here, right? Then when I subtract the first equation from the second, I assume this is constant and it drops out. So even though they give you A, that pre-exponential factor, 3.4 times 10 to the 14th reciprocal seconds, you don't need it to solve this. With the Arrhenius 2-point equation. Do you understand that, or should I write it out for you?
I think I understand it. I think I got confused because I thought that we had started with it as K1. So that's why I was confused.
Yeah, so the assumption is that that A factor back here is independent of temperature, which is not quite true. So you pick any temperature and that changes K. So then when you look at it that way, you're looking at an infinite point function with as many values as you can think of. Whatever temperature you can think of, you write it down or you put it down. That's the independent variable. And that dictates what the dependent variable is going to be, the K. And you're assuming that this pre-exponential factor is constant through temperature. At least the temperature ranges we use in Chem 201, that's true, but it's not strictly true. So when I write out the equation in this form here, then I can write out another equation for any other temperature. And so when I subtract one from the other, that's where I get the ratio of K1 over K2, because I use that law of logs. And then I can just bring down the EA over R and 1T1 minus 1 over T2. And these guys, since they're the same, if I subtract one from the other, they cancel. And so this is where you get the Arrhenius 2-point equation. And it doesn't have that pre-exponential factor A in it anymore, because you assume that A is constant over the temperature range that you're using this equation.
Okay, got it. Thank you.
Yeah, sure. So they give you extra information here in the hopes that you'll go back and you'll study this and you'll rationalize and reason through that yourself. And I think it's a tall order, but it's good if you got that all by yourself, then you're doing really well, I think. All righty. Any other questions? No other questions?
Yeah, can you go over number 20?
Yeah, let's take a peek at what number 20 looks like. Okay, number 20, I'm not going to go over yet for a couple reasons. We haven't discussed that, and that was sort of the topic of our discussion today is reaction mechanisms. So I'm going to hold off on that. Plus, your homework's not due, the last one's not due till tomorrow night, right? So I wanted to give you guys a chance to work through that without me, giving you any hints on it. So are there any other questions on anything that we looked at so far? All right.
Is your equilibrium homework still due Sunday, or is that pushed as well?
Well, let's see. Let's see how much time we devote today to our discussion on equilibrium. and on Wednesday. If we don't get through it on Wednesday, we could push it.
Okay.
Yeah, so yeah, keep on top of it. Remind me. We'll work stuff out, make sure we keep the emphasis on learning and not so much worrying about points, even though everyone does it. And I understand your concerns and stuff, but. All right. Any other questions? Five, four, three, two, one. Okay. All right, then what I'd like to talk about now is kind of a recap of what we talked about last Wednesday in our discussion, and then we can go on to mechanisms. So last time we were talking about the rate law and how a rate law will give you so much information, but not everything. So here's a typical rate law for some reaction that it describes. In general, we put an X here because we don't know the pre-exponential factor until we have some experimental data. And we can use that either in the tabular method or the method of initial rates to find those pre-exponential factors, or we saw the strength of the integrated rate law and how you could possibly use that in a graphical method to determine what the power dependency, that X of concentration of a reactant is and how it affects rate. So we have essentially two ways to get at that rate law. But we, last time we mentioned that an experimental rate for a reaction also depends on this constant, which isn't constant always. The constant changes for various things. Like if you change any one of the condition parameters, it changes. If you change the reaction environment so that the surface area is different, then K will change. If you add a catalyst, K changes. Or if you change the temperature, K changes. So we mentioned that K is not a constant with temperature usually, unless it's a 0th order reaction. All right, so here's an example for this reaction where K is dependent on temperature. And so we wanted to see what were the factors involved in reactions that will allow us to understand this K dependence on, for example, temperature. So we said, well, let's consider a very simple theory called the collision theory, which allows us to envision how reactions take place when reactants come together, they collide, bonds are broken within the reactants, and new bonds are formed within the product. So that's all the picturing of the collision theory. And how does that help us understand why at higher concentrations rates could increase, or why at higher temperatures the rate could increase? And so collision theory allows us to rationalize those things. Now, just because something collides, it doesn't always react. There's also an energy criterion involved. And so after thinking about the energy criterion that's involved, Arrhenius decided that there's really an important energy in a collection of molecules that are about to react. And that is the minimum amount of energy needed for a successful reaction. He called that the activation energy. And he puts that to a picture in a potential energy surface of how energy changes as reactants come together to form products. So we defined a lot of those energy criterions in this picture. For example, This here is the energy of the reaction as the reaction proceeds from reactants to products. And you can see that the largest energy that needs to be surmounted to get over that hump is EA, but it's actually the smallest possible energy. So that's the activation energy. The geometry of the reacting species is called the activated complex or the transition state geometry. And it's where there's a simultaneous breaking of reactant bonds and a formation of product bonds. So that activated complex has bonds breaking and forming at the same time, and that would give me the minimum amount of energy that's required for that reaction. There's another interesting energy difference here, and we pointed that out for exothermic reactions. That's going to be negative. For endothermic reactions, it's going to be positive. All right, so we talked about that, introduced it, and Arrhenius said, man, I wish there was some math I can use. And Boltzmann says, hey, I know of a mathematical function that allows me to talk about a collection of particles, let's call them molecules, and the distribution energy
It would
within.
be hard to quantify that because it'd be hard to tell how much dopamine a baby has, you know. But yeah.
Yeah, I'm sorry, was there a question? I guess not. All right. Any questions or comments? All righty. Then Boltzmann set out this distribution, and it makes kind of a nice picture if you just look at this plot down here. And this is two different plots overlaid, one at a lower temperature and one at a higher temperature, but it represents a collection of, let's say, molecules. So the area under each one of those curves represents the number of molecules, so the areas are the same. We see that for the higher temperature, this guy right here, the area under that curve is the same as the area under the lower temperature curve. That has to be true because they represent the same collection, and that area is related to the number of molecules that it describes. So when you heat up that collection of molecules, the distribution of energy shifts to the right. So the curve kind of hunkers down a little bit, but the average energy shifts to the right, and that should make sense. So here's the average energy for the cooler collection, and say this is average for the cooler, and this is the average for the hotter. So on average, molecules are moving faster at higher temperatures. So if we look at any specific reaction, it's going to have some activation energy that relates to that specific reaction, and we'll just call it there at that point. It could be anywhere. And you could see that the area under the curve for the hotter description of energies is larger for that EA or greater than it is for the cooler one. So in other words, there's a higher fraction of molecules that have that critical, that crucial, that important energy at higher temperatures than at lower ones. So this is great. This is a great mathematical formula that Arrhenius can use to describe how temperature and activation barrier affect the fraction of molecules that are at that temperature and have that energy or greater. So Arrhenius uses the Boltzmann's distribution in his new definition of the K, let's get it over here. As soon as my thing stops messing around. I got this gaming mouse online, and it's got all these extra buttons, and if you hit a button by mistake, it just freaks out on you. So that's once in a while, that's what happens. But anyway, here's Arrhenius's new definition of K. It involves that Boltzmann's distribution. So it takes account for changes in activation barrier, which is reaction dependent. And it also takes into account any changes of temperature. And it says all the other factors that are important in reaction rates, or the rate constant, as long as they're held fixed, I'm just going to lump them into another constant, A, called the pre-exponential constant, and leave it at that. Let's just assume that no one's changing the surface area or changing any conditions specific to that reaction that may affect anything that goes into A. Now, what are some of those important factors that go into A? We mentioned back here that the orientation factor and the number of collisions are important. And so we had a picture here saying, yeah, if you have a head-on collision between the reactants that are favorable towards the reaction you're describing, then you can have an effective collision. But there's a lot of possible collisions that aren't going to be effective for that particular reaction. So that's some of the factors that go into that pre-exponential factor A. We talked about them, and we're going to assume that they're fixed until further notice. So if you study this again in graduate school and you want to kind of zone in on other factors that are important in reaction rates, then you may look at them and mathematically model them and incorporate that into the A, just like we have done so far. Then we introduced the Arrhenius 2-point equation because we were saying, oh, well, you know, even though this is an infinite point equation where you give me a temperature and then that'll change my constant, and I can calculate that constant as long as I have the pre-exponential factor and the activation barrier for that specific reaction. What if I just wanted, I just had 2 points, then that collapses. I take one from the other and I get what's called the Arrhenius 2-point equation. And in our problem that we looked at, you saw the utility of that 2-point equation, gets rid of that pre-exponential factor. And then we talked about how that's related to the slope of a line. Again, you know, thinking that this equation is an infinite point equation. There's as many KT points as you can think of. So in this form of the Arrhenius equation, you see, to get a straight line, you're going to have to take the log of K, and you're going to have to plot that against 1 over T, which is done down here. Then it gives you the form of a line, which you can then fit, calculate the slope, relate that to the activation barrier if you wanted to, or the pre-exponential function A, and calculate that in its relationship to the intercept. All righty, so you were to play around with that, try this problem, and that's pretty much where we left off last time. Any questions so far on that quick review? All right, so today we're going to finish off the rest of the chapter in our discussion and maybe get on to equilibrium a little bit and see what's up with that. But the first exam is going to be mainly on this first kinetics chapter. We're going to spend a lot more time on this than equilibrium. We're going to spend half the time on equilibrium before that first exam. All right. So let's move on to the next topic in our kinetics chapter, which is mechanisms. So thus far in your chemistry career, you've looked at reactions where some reactants get converted into products. But we've never really thought about what the detailed step-by-step procedure is when taking those reactants and making the products from them. What are the actual bonds that are broken? Are there any things that are formed but then get consumed, which would be called intermediates? And what happens to them? So people thought about this, but since people can't see atoms, it remains to be a theory about atoms. We have the atomic theory, which can't be proven without, within a reasonable doubt, because we just can't see that. And it's the same thing with mechanisms. Mechanisms are proposed to explain the detailed conversion of reactants to products, but you can never prove a mechanism. You can only prove a mechanism to be impossible, and therefore tell everyone, the scientific community, that mechanism needs to be thrown out or it needs to be modified. So that's what we're getting into now. Now, this is a second semester general chemistry class. You will not be asked to propose mechanisms all by yourself. What you will be asked to do, of course, is to understand what they are and what they describe. But you'll be asked to look at mechanisms and decide whether they meet the basic criterion for possible mechanisms, or that they're ridiculous and they should be thrown away. All right, so that's your job. You don't have to come up with mechanisms, because mechanisms are based off of a lot of experimental and scientific experience. Mechanisms in organic chemistry, for example, can have many steps, pages and pages, hundreds of steps for one reaction. Or reactions can have one-step mechanisms, and anything in between. The number of steps you guys are going to be looking at is probably 1, 2, 3, maybe 7 steps. But that's about it. So anyway, what are these mechanisms? Mechanisms are detailed descriptions of reactions that can't be proven without a doubt, but are taken to be true as written unless they can be disproven, in which case they're thrown away or they need to be modified. We're just going to throw them away most of the time, I think. So what are these mechanisms made up of? They're made up of what's called elementary steps. So these are like the laws for this reaction. It's kind of like a 10 commandment thing. This is what happens, and then this happens, and then this happens, and that's the way it is from now until eternity, unless it doesn't agree with experiment. If it doesn't agree with experiment, then you have to throw it away, like we said. So it's made up of elementary steps, and it describes in detail what happens to the reactants to make products. And it also may involve what's called intermediates and also catalysts, which I didn't write here in this description. But anyway, back to the mechanism. There's 3 basic elementary steps. One is unimolecular, two bimolecular, and the third one is almost never ever used because it's so improbable, is termolecular. And the names coincide with the meaning really well. Unimolecular means one molecule in the reaction. Bimolecular means two have to come together, and three is for termolecular. And now just remember, you have to have three molecules or atoms, not only colliding together, but colliding in the correct orientation. What's the odds of that happening? Very little. So term molecular is not used very often, and anything higher than that is even crazier. So there's our definitions of the three different steps. Let's take a look at what we mean by intermediates and the elementary steps, and what consequences that has in terms of rate laws and the things we've been talking about in kinetics. So an intermediate, what is that? We see an intermediate could be part of a mechanism, and it's found in the elementary steps. And an intermediate is something that's produced in one of the elementary steps, but then consumed in a step that follows. So for example, if I have some reaction A plus B goes to C plus D, then I have another reaction. Say this is step one in my mechanism. Then step two, I'm going to have D goes to F. So the overall reaction is found when I add up all the steps, all the elementary steps in the proposed mechanism. I see that D was produced and also consumed. And the overall reaction that this was supposed to describe, oh, I screwed up something there. Okay, we're back. Looks something like this. So this is the reaction and how it's described. And this is what you've been doing so far in your chemistry career, just looking at some reactants and some products. And so if I wanted to, for example, write the rate law for this, it would be something like rate equals K times concentration of A to the X times B to the Y, and so forth. So that's the reaction that you guys been using all along. This new stuff over here is the mechanism. And one thing a mechanism has to do is add up to give you the reaction, the overall reaction that this mechanism is supposed to describe. And in this case, we see the definition of an intermediate, something that's produced in one step and then consumed in another, so you never even know it was there. Any questions on what an intermediate is? All right, well, we're going to get some more practice with that. But I'll just throw in here right now the difference between an intermediate and a catalyst. So a catalyst is something that speeds up a chemical reaction, but it doesn't get consumed, right? So an example of a catalyst could be G. So if I add a catalyst to this, G's there, but then at the end, it's produced again. So again, it cancels out and you don't see it in the overall reaction, but it's definitely different than an intermediate. A catalyst is introduced in the reaction, but then is produced later on, so there's no net consumption. All right. Now we get to the three possible elementary steps that we're going to consider, knowing that this one, that's pretty suspect. We're not going to be using that very often. So if an elementary step is what we call unimolecular, then it has one reactant. If it's bimolecular, then it has two reactants. Could be two of the same or different. And three termolecular has three reactants. Now, remember before we said that if you're going to find the pre-exponential factors for some rate law, so we know that the general form of rate laws looks something like that. This pre-exponential, I'm not pre-exponent, this exponent here, this power dependency has to be determined experimentally. And you could do it the graphical method using integrated rate laws, or you can use the method of initial rates where we have tables of experiments with different concentrations and correspondingly different rates. So we needed to get experiment to find that. With mechanisms, we can look at the stoichiometric coefficients in the elementary steps, and we can propose rate laws for the elementary steps that use those stoichiometric coefficients as power dependency, because these are elementary steps and they are believed to take place as written. In other words, two A's collide to form a C. So there's got to be that bond broken, and that's all that can happen. And then new bonds form C. So because these are elementary steps, we can use the stoichiometric coefficients to say what that exponent or that power dependency is. All right, any questions on that? All righty. So we have a couple examples, one for a unimolecular elementary step. That's where we take one molecule and it makes a different one. Bimolecular, like we said, we're going to take one molecule or atom in this case and another molecule and make something else. So that would be an example of a bimolecular reaction and a bimolecular elementary step. All right, so now we're going to start looking at mechanisms. So the usual thing is all right, so far in your career, you've looked at a lot of reactions, a lot of reactants and products. So here's another one. So consider this reaction. And as soon as I see this reaction, I know the form of the rate law looks like rate equals K times concentration of NO2 to the X times CO to the Y. But now somebody has done the experiment, tabular method or whatever, and they found that the experimental rate law for that reaction is this. Maybe it was the integrated rate law they used or whatever. So we see that X is 2 and Y, what's Y? Anybody there?
0.
Yeah. Thank you. I got to check once in a while. You guys should just holler or something, just so I know that you're out there. Okay, so I have X and Y, that has to be 0. All right. Now, someone came along, I don't know who it was, maybe the publisher of your textbook, maybe some scientist working in the lab, and they said, okay, we're going to propose this mechanism. And then you're like, who cares about mechanisms? Well, the thing is, if you can come up with a mechanism for a reaction, then you have more power over controlling that reaction, especially the speeds. You know, what do I need to know about that reaction to make it faster, make it slower, make it more efficient, or whatever? And so we're trying to describe reactions with what we call mechanisms, so we have more power to dictate over them. I probably should have mentioned that purpose back when we introduced mechanisms. But anyway, I did it, so I'm okay. All right, so someone proposes a two-step mechanism. They say, okay, I think I know what's going on with this reaction. I think that two NO2s come together and they make an NO3 and NO. And then what happens next is NO3 adds to the CO and I get NO2 and CO2, right? Now, this person either says that this one I propose is a slow step and this one, the second one, is the fast step. And they may know that because they did some experiments, or maybe they even calculated the rate constant for step 1 versus the rate constant for step 2. And they see which one's bigger and smaller. What would you guess, you guys? Let's see if you can answer this. I'm telling you that step 1 is slower than step 2, which is faster. What do you think the relative magnitude, I'm using the word magnitude, of K1 is compared to K2? Anybody?
Would it be higher because it would be a steeper slope since step 2 is happening much faster?
Well, it says right here the answer. K2 is going to be greater than K1. Why should that be? Because you know this is slower, so the rate of the slow step should be slower than the rate of that second step. I'll just call that rate 2. This is slow. And you know that that's going to be proportional to K times some concentration things here in both cases. So I'll call this K slow, call this K2. And if this rate is faster, then chances are this rate constant is going to be larger, which is going to make that R larger than this case here. So when you see, sorry, I did it again. So when you see a slow step in a mechanism, that tells you something about the relative rate constant for that step compared to the other steps. Another way to look at it is through activation energy. We know that that K, the Arrhenius K, let me write it over here. It's starting to get a little sloppy. K equals A times e to the minus EA over RT. So we also know that K is not only affected by temperature, but it's also affected by the activation barrier. So if both of these steps are at the same temperature, then maybe they have different activation barriers for those steps. And the one with the slowest step is most likely to have what activation barrier compared to the faster one? Anybody? The relative EA of the slow step compared to the fast step.
It's going to be higher.
Yeah, that would make sense. Absolutely. Okay, so these are just other hints. But anyway, this is our first mechanism. We're just starting to get to learn what's going on. This is the reaction that it's describing. up here. This is the breakdown of that reaction. Somebody says they think they know what's going on in the detailed process where you take these reactants to make those products. And they said that that first step is slow. So it begs the question as to who cares about which one's slow? Why is that important when talking about rates of reaction? Why is it important to identify the slow step?
Because the slow step is as fast as the reaction can proceed.
Yeah, so you know that, or you've probably seen that from, I don't know, assembly lines in factories. If you want to speed up a process, you see where the bottleneck is. And if you can open that bottleneck a little bit, that's going to open up the overall rate of that process. So like factory workers, chemists are interested in identifying the bottleneck or the slow step, because once you identify that, then maybe you can do something about it and propose possible experimental updates to make reactions faster. And so this is kind of why, this is another reason why someone would want to study reaction mechanisms, because the more you understand about a process, the more power you have over that to dictate how it's going to happen. All right, so we're just looking at this. So it looks reasonable right now. Okay, this is step one, step two, fine. I recognize the reactants in the products. In fact, I can go through the whole mechanism and I can identify each one of those as either a reactant, a product, an intermediate, or a catalyst. Okay, so let's go through and just take a look at it. You know, we'll take our time. Step one has an NO2 here. What is that?
Product.
That's a reactant. See, it's right there.
Yeah, that's what I meant.
Yes, and you were right. So this one also same. That's a reactant. What's this guy?
Product.
Intermediate.
Yeah, it's an intermediate. So it's produced in a step, and then a following step, it's consumed. So when I add up these two steps, it gets crossed out. And remember, any mechanism, when you add up all the steps, it has to equal the overall reaction it describes. That's one of the tests that you're going to use to decide if a mechanism is possible. If it doesn't add up, then you got to throw it away.
Where does the NO come from? Is that like the ones that haven't formed NO3 yet, or?
Yeah, so it looks like if I take the two NO2s
Uh-huh.
and I react them, then one of the oxygens from an NO2 goes to the other one. And what do you have left? You have an NO3 and an NO.
Okay, I see.
Yeah. So, and that's one of the products. So now we have, in step one, a reactant plus a reactant gives an intermediate and a product. Step two, I have the intermediate reacts with, what's this?
A reactant.
Reactant.
Yeah, it's a reactant. Very good. And I get that. What's that?
It was a reactant, but now it's a product.
Yeah, yeah. But in the, right, you're right on both accounts. In step two, it's a product of that elementary proposed step. but in the overall reaction, it's a reactant. So some of the reactants are getting reproduced in this mechanism. And then this last guy, what is this?
Product.
Yeah,
Product.
good, great. So that's pretty much the ins and outs of a mechanism. Now, if I add it up, I cross out the intermediates, right? And I add up the other guys, I got to cross out one of these. And I see I get, when I add them up, I get an NO2. Sorry, it's kind of sloppy. Plus a CO goes to NO plus CO2, which is this. So it does add up. Okay, so that's the first criterion that you should check for any proposed mechanism. Does it add up? And being able to identify intermediates is helpful. All right. The next thing you have to do is to identify the slow step that's in the mechanism and check to see if the rate law that you get from the slow step agrees with the experimentally determined rate law. All right, so remember, rate laws for elementary steps you can get without experiment. You just look at the stoichiometric coefficients. So what's the rate law for step 1? Anybody?
NO2 to the first power
There's 2 of them.
times NO2 to the first power, or does that make it to the
Yeah.
10th?
Yes, you're right. You are right. And it does make it, another way to write that is just put NO2 to the second power. So you're right. Any questions on that? So I can use the stoichiometric coefficient here, 1 and 1, that's 2. So there's 2 NO2, so it's NO2 squared. And so that is the rate law that I get for the slow step. And see, it agrees with the experimental one. So your conclusion for this is that this mechanism is possible. Is it true? I don't know. Nobody really can prove that, but it's possible. Any questions on that?
I have a question about NO2.
Uh-huh.
So if it's a reactant but also produced again, how come it's not a catalyst?
Because it's not considered to be a catalyst because it's a reactant. And you can use reactants at different rates. And it's defined as a reactant because someone said, okay, let's take a look at this reaction here. And we're going to talk about the mechanism for this reaction. So when they did that, they defined NO2 as a reactant, and it's not a catalyst because it does get consumed, but not all of it. Some of it gets reproduced, but then that can get, more, it can get consumed after that.
Oh, okay. Oh, I see. So it's because catalysts don't get consumed, but
Yeah, no net consumption. A catalyst can be consumed, but it has to be reproduced. So, I mean, you could look at that NO2 as, oh yeah, it has a catalysis nature to it. And there's a lot of experiments that do that. They actually produce some products that then can even catalyze the reaction. But we don't call it a catalyst, we call it a product.
Oh, okay.
It takes precedence over the definition of the intermediate. Okay, any other questions? All right. I'm going to move down to this next example. All right, now we're going to move on to another example of a mechanism, and then we're going to go through the same steps to see if it's a valid mechanism. We're going to look at to see whether it adds up, and we're going to identify the slow step in the mechanism and see if it produces a rate law for that slow step that agrees with experiment. But there's going to be a twist at this point in our analysis, and you're going to be responsible for understanding this kind of a curveball and working through it. All right, so here we have our next reaction. And someone was nice to go to the lab and determine the experimental rate law for that reaction. Someone else proposed a two-step mechanism for this. The first step's fast, the second slow. And now we have to go through our checklist to see what's going on as far as whether it's possible. All right, now I go through and I can identify that as a reactant. That looks like a reactant. This one there's not included, so maybe it's an intermediate. Yeah, it turns out that this is an intermediate. So that cancels. Then I get another reactant, and then I end up with my products. So if I add this up, then I do in fact get the reaction that this mechanism describes. So it does add up. That's good. Now I go on to the next one. I identify the slow step. All right, they told me. Now, in all your problems, they're going to tell you which one's the fast step, which one's the slow step, or they're going to give you relative magnitudes of rate constants or activation barriers for you to infer that, which one's the slow and the fast. In other words, since this is slow, then these rate constants are going to be bigger than this one. Okay. Anyway, we identify the slow step, and I see that the rate law based off of that slow step is right here, slow. And at first glance, it doesn't look like this experimentally determined rate law. Now, the problem with this is that the rate law that corresponds to the slow step, it contains an intermediate. This guy right here. So scientists know that experimentally determining the concentration of intermediates is a difficult task because intermediates don't hang around that long. And if they're not colored, then you can't use a Beer's law analysis and so forth. So it's really hard to track changes in concentrations of intermediates. So what they say is that, well, is there a way to look at this rate law and somehow rationalize why this mechanism can still be possible? And there's one way to do that, and it occurs when there's a fast step that precedes the slow step. So it's before the slow step. And what scientists say is, well, if it's faster than the slow step, then it's going to reach equilibrium fairly quickly relative to the slow step. And that introduces the definition of equilibrium. For something that reaches equilibrium, as you may recall from Chem 200, the rate of the forward reaction equals the rate of the reverse reaction.
So are you saying that fast steps usually don't create intermediaries?
No, in fact, in this case, it did. What I'm saying is that fast steps come to equilibrium while the slow step is still taking place. So what does equilibrium mean? That means that for this fast step, the rate forward equals the rate reverse. Or in other words, I'll just put it up here, rate forward equals rate reverse. So for that first step, the rate law forward is going to look like some rate constant Kf times the concentration of NO times the concentration of Br2, right? And I know that they're first power for both because the stoichiometric coefficients are 1. And since this is an elementary step, I can just look at those stoichiometric coefficients and know that exponent in the rate law for that step. All right, everyone see that? And so that K forward, really, I should write that as K1. Okay. That's what it is down here. Now, this guy down here, the reverse reaction is K minus 1. That's the rate constant for the reverse reaction. So the rate forward equals rate reverse. So this should equal that K minus 1 times NOBR2. That whole thing equals the rate reverse. Any questions on that? All right. So what's done now is they say, okay, this rate law that I got from the slow step down here has this term in it that corresponds to the intermediate. And that intermediate is not in my experimentally determined rate law. And people say, oh, well, geez, it's not surprising because intermediates are hard to experiment with. Well, using that idea that the previous step comes to equilibrium, can I solve for that intermediate and substitute it back into this rate law and see if it makes more sense? So I can do that. I can solve for NO Br2, the intermediate. I find that that equals K1 divided by K minus 1 times NO times Br2. I make that substitution in here. I see that NO, well, I substitute in, I get K2 times K1 over K minus 1 times NO squared times BR. And then I say, well, geez, all those Ks, they're just constants. So I'll just lump them together and I'll just call that K. And now I see that the rate for the slow step equals K times NO squared times BR. And that's what they found experimentally. So I can't throw away this mechanism. It's possible. I have to accept it. So it's just a little more math to prove this type of mechanism. Any questions on that? No questions. All right. Well, I think that's explained in the next few slides, so you can go back and study that and look at the video. This slide here talks about a catalyst. So here I have some reaction, and it has an activation barrier, and it's a one-step mechanism. So there it is. There's the mechanism. It's the decomposition of hydrogen peroxide, and it's very slow. If you've seen bottles of hydrogen peroxide in the pharmacy, they come in brown bottles because they're affected by light. Light speeds up this degradation reaction. Otherwise, it's fairly slow. I can add a catalyst, this bromide. It changes the mechanism as well as speeds up the reaction. This catalyst is used up, but then it's produced later on. So that's different from an intermediate. Okay. I have hydrogen peroxide in this mechanism as a reactant. This guy over here is a catalyst, H+, because it's consumed and down here it's produced. Okay. So I have two catalysts, Br minus, H+. Br2 is an intermediate, and H2O is a product. Okay. Oxygen's a product. And it adds up. So this two-step mechanism with the catalyst adds up to give you the overall reaction that it describes. But what's interesting about this is now we can show what happens to the potential energy surface when a catalyst is introduced. For this example here, I have energy reaction coordinate. I have the two different reactions, the catalyzed reaction and the uncatalyzed reaction overlaid, so they're on top of each other. I start out with these reactants and catalysts here, and I see that for the catalyzed reaction, the activation barrier is reduced, and it goes from a one-step mechanism to a two-step mechanism with two different activation barriers. The first one is larger than the second. So guess which one is the slow step?
The second?
No, the
Oh.
first. The first has a bigger EA than the second.
Oh, right. That makes sense.
Yeah, it makes sense. See, it's very confusing, and it's easy to jump to the wrong conclusion. And it's great if you do, because I think that's a great way to learn. You get it wrong and you say, wait a second. And then you think through it, and then it makes sense. I wish I had a nickel for everything I got wrong. I'd be pretty rich. But that's not the point. The point is realizing that you got it wrong and think through it and get it right. So yeah, this is the how a potential energy surface would change for a uncatalyzed versus a catalyzed reaction, which also changes the mechanism. So we're getting a deeper, better understanding of reaction rates by analyzing mechanisms, specifically identifying the slow step in the mechanism, the bottleneck. So maybe we can add a catalyst to speed up the reaction and so forth. Now, the other slides here, heterogeneous catalyst versus homogeneous. Okay, so what? Big deal. Heterogeneous is two different phases, solid, liquid, gas. Adsorption is when you have a solid that interacts with a reactant to weaken its bonds and therefore make it easier to break. So, and there's all different types of catalysts and biological catalysts. It's called the enzyme. So enzymes have a structure that interact with a reactant. This is called a substrate in biolingo. It's a reactant, and it weakens it somehow so it doesn't need as much energy to break, and therefore lowers the activation energy and speeds up the reaction. But you get the catalyst back again, and the rest you can read. So, that's pretty much the end of this chapter. Now you're ready to do the homework, which is due tomorrow night. So try to work on that tonight. If you have any questions, then ask tomorrow if you can, and I'll try to get back to you as soon as possible. If you post a question in our discussion, or if you can wait till our discussion tomorrow, then definitely ask then. So, anybody have any questions? I'm going to end our discussion there and just hang out until everyone's gone. Okay.
All good. Thanks, Professor.
Hey, anytime. It's my pleasure.
Thank you.
Yeah, thank you. Keep up the hard work.
Thank you.
You got it.